Welcome to Climate Chat. I'm your host, Dan Miller, with my co-host, Leon Simons. And we have a very special returning guest, Dr. René van Westen from the University of Utrecht, who's going to be talking to us today about a very interesting and important new study that he led on how the AMOC, or the Atlantic Meridional Overturning Circulation, kind of more generally known as the ocean conveyor belt that brings warm water from the tropics to northern Europe, how the slowdown and potential collapse of that current is not only dependent on the amount of global warming we have, but the rate in which we're warming. And that has very big implications, and we're going to talk about that. But even though this is actually, René, you are, I think, our first guest, besides Leon himself, who's returned 4 times to the Climate Chat. So welcome, 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 welcome. And
thank you.
Even though you've been on many times before, some of our viewers will be seeing you for the first time. So perhaps you could start off by just giving us a little bit of your background.
Yeah. Thank you again. To be part again of this very nice conversation with you, Dan, and with Leon. So my name is René van Westen. I'm a postdoctoral researcher at Utrecht University, and I have an expertise in physical oceanography, high-resolution modeling, and we're currently investigating the stability of the AMOC, so the large-scale Atlantic Ocean circulation. Whether it will collapse under present-day climate change or future climate change, of course, is a big question, because the implications are huge for global society, particularly for Northwestern Europe.
Okay. And Leon and René are both Dutch. And so, Leon, you actually know a lot about René's university. Can you just give us a little bit of an overview? Because it's actually a leading university in climate research, and I think a lot of people are not aware of that.
Yes, thank you, Dan. Yeah, I did some research with the University of Utrecht myself in Ethiopia. It was mainly focused on health. I think last decade, the late Marjan Minnesma, for example, she organized in Utrecht a meeting with many climate scientists, including James Hansen. And I was also there. And then there was the preparations of the climate court case were held there. And of course, this climate court case is really, it made, in a way, climate the Paris Agreement and other agreements like that legally binding in many ways, because they wanted up to the Supreme Court. It was against the Dutch government. And I think many things are happening in Utrecht, right? So maybe you can talk a bit about the importance of Utrecht and of your university.
Yeah. So our university has quite a broad experience in all different kind of fields. So we have also a very active chemistry department within the institute. So we're part of the Institute for Marine and Atmospheric Research, Utrecht, for short, EMAU. So we have people from chemistry who have like world-leading laboratories to measure all different kind of isotopes. We have a very active land ice community within EMAU. So they're also developing and participating in all different kind of development of ice models, which are used to make these kind of projections for the Greenland ice sheet and for the Antarctic ice sheet. We also have collaborations on the atmospheric component with people, also from people from the KNMI. So that is the Royal Dutch Meteorological Institute, which is only like a few kilometers away from Utrecht University. And we also have the physical oceanography people, both on plastic, so that is tracking where plastic will end up, but also on the AMOC stability and other stability of other major ocean currents.
Okay. So why don't we dive into your latest paper here? Let's see if we switch here. And it's titled Failure to Track a Stable AMOC State Under Rapid Climate Change. So why don't you just start off and just give us an overview of what your research has shown?
Yeah. So maybe I can also give you like a very basic introduction also from the past times that I was on the show, then, if you do like that, because that gives you a little bit more of an emphasis what we've done over here. So back in 2024, we did like an experiment in which we added fresh water to the North Atlantic Ocean. So you could imagine that the Greenland ice sheet is melting. It pours a lot of fresh water into the Atlantic Ocean, and this destabilizes the AMOC eventually. And if that happened, you will get like tons of large-scale consequences for the planet. So you get like an adjustment of heat. You get a lot of climate impacts over northwestern Europe. You get this massive cooling, very cold and harsh winters, more intense winter storms, less summer precipitation, and higher sea level due to a collapsing AMOC. So that was what we did first, but that was an idolized experiment. So we added fresh water at a very slow pace until there is like a critical level for which the AMOC starts to collapse. So if you add too much fresh water, this whole circulation becomes unstable and then it collapses. But what we didn't consider then was like the effects of climate change, because the planet is also warming at the same time. So in the study which was published last year, we tried to assess like at which level, which global warming level, or in which year will the AMOC become critically unstable under global warming. So we did the same kind of experiment, but then added CO2 and other greenhouse gases to our atmosphere. And what we actually found from like 25 different climate models is that the AMOC becomes unstable at about 2.5 degrees warming, which happens around 2060 in those climate model projections. And now we come again with a slightly more nuanced view in that regard. So these kind of years and these global warming levels, they still hold. So it is not like, oh, this is again not true. But what we actually found is that not the global warming level determines whether the AMOC becomes unstable, yes or no, but actually it is the warming rate that determines whether the climate or the AMOC system becomes unstable. And of course, it becomes unstable at a given level at about 2.5 degrees warming, but that is not the controlling factor. So if you would reach this 2.5 degrees warming, for example, by 2200, then the AMOC would very likely be still stable, and therefore you won't see any collapse. So it completely shifts the picture from like a fixed magical temperature level you can so imagine to a more of a temperature rate.
Okay. Okay. And actually, there's a graph here that kind of shows what you're talking about. Maybe you could, this is a key figure from the paper. Maybe you could walk us through this.
Yeah, so I think this is one of the most important figures of the entire paper, because here you can see two different kind of simulations that we have done. So on the horizontal axis, you can see the amount of atmospheric CO2 concentration. So we start from pre-industrial values, so that's at 280, so that's all the way to the left. And we will increase this up to 4 times CO2, so to very high levels, that is all the way to the right. And we increase the CO2 concentration in a linear rate. So we have two different cases. So we have the black curve, which increases at half ppm per year. So that is at a factor of 5 times slower than present day values. So you run the entire simulation, and what you see on the vertical axis, that is the AMOC strength, which we measure in like a volume transport. So this is like, we start at values of about 30 million cubic meters per second, what we also call 13 Sverdrups. So we start at that level, and we let the atmospheric CO2 concentration rise in our simulation. And to our big surprise, the AMOC remains stable all the way throughout this 4 times CO2. So of course, there are a lot of fluctuations. There is a lot of interannual variability going on, but the AMOC is not collapsing. So it remains like at a very consistent strength throughout this entire simulation. And at the very end of the simulation, we actually reached global warming levels of about 5.5 degrees warming. So that is like a lot of warming going on with still having a stable AMOC. Then we did like a follow-up experiment. So that is the blue graph. So everything remains the same, but we're actually adding CO2 at a faster rate. And what you now see is that they are starting to diverge. So there is nothing else going on, only the speed is different. And now you see that the AMOC is actually going a different route. It is actually collapsing. And the star here in this graph indicates the onset of the AMOC collapse. So from this point on, no matter what you do, the AMOC will always collapse in this simulation, and the AMOC continues to go down and further weakens over time. So that means that you have two different kind of pathways. If you do it at a very slow pace, like the black curve, you can have like a very stable AMOC state. But if you do it more rapidly, like the present day case, eventually the AMOC may collapse under climate change. And these stars happen actually at a temperature level of about 2 degrees warming. So again, highlighting the point that I made in the beginning. So this happens about the 2 degree mark. But keep in mind that this is not like a magical boundary for which the AMOC collapses, because the black curve has unstable AMOC states up to 5.5 degrees warming. So that is way above this temperature level. So that really highlights that the rate determines whether the AMOC becomes unstable, yes or no.
And is this really a CO2e in a way? I mean, equivalent CO2, or is it CO2?
No, it's only CO2. Of course, you could also imagine that you're adding methane and other greenhouse gases. But to make everything as simple as possible, we only varied one greenhouse gas. But of course, for the actual case, what's going on for the present day climate, we're also adding the very powerful and potent methane greenhouse gas, which is about a factor of 28 stronger than CO2 equivalent. We also have like laughing gas and other greenhouse gases, which are of course sometimes much stronger compared to CO2. So in the end, what you can actually do is just convert everything like to a global warming rate. So that can actually help you to see what the entire globe is doing, rather than only looking at CO2 emissions. But of course, the higher CO2 emissions you have, the more warming you get.
Because this star here is, you said, is at 2 degrees of warming. It's showing 650 parts per million of CO2. We're going to be hitting 2 degrees next decade at around 450 or so parts per million of CO2. But of course, the CO2 equivalent is more than a doubling of CO2 from pre-industrial.
Yeah.
So
yes.
2 degrees is on its way very, very soon. And
yes, that's exactly
this star area. So we're going to get into that a little more. Leon, did you have a question?
Yeah. So I think with just greenhouse gases, so not taking into account aerosols, the current CO2 equivalent is already above 560 parts per million. If you use the IPCC methodology, and also what we did with global warming in the pipeline, we assessed it as well, and we came to the same numbers. But maybe I missed it, but you didn't mention the rate of warming in degrees Celsius per decade, did you?
No, and not specifically here. So by heart, so the black curve is warming about 0.03 per decade. So that is quite slow. And the blue curve is warming at a rate of about 0.15 per decade. So that is about a factor of 2 slower than present day. But we also had like a simulation in which we increased the atmospheric CO2 concentration by 5 ppm per year. And that has a rate of warming of about 0.3 per decade. So you can also see it in the paper that we have done more simulations than those. What you were also mentioning, Leon, about the aerosols, because aerosols also have like a cooling effect. So therefore, if you include those as well, everything becomes very complicated. So therefore, we only varied like one parameter in our simulations, the CO2 emissions or the concentration, such that you can make like a very nice comparison between the two.
Because I recall the 0.3 in your paper. So you're saying this particular graph is actually 0.15 per decade?
The blue, yes.
Which is the old amount of warming. 0.18 was, pre-2015.
Yes, so if you also can, so you have the paper in front of you then, right?
Yeah.
Yeah. So if you go to figure 1C, you can actually see
the other one.
Yeah, you can also see the other one. Yeah, so this panel C, so at the bottom left, so those are all the simulations that we have conducted. So the black and the blue curve we already discussed, so they're essentially the same. But here you also see a red curve. So that one is increasing even at a faster rate in terms of atmospheric CO2 concentration. So that is increasing by 5 ppm per year. So that is a factor of 10 faster compared to the black one. And there the AMOC also collapses. So you're also just hitting like a critical warming rate. So the red one is even above that one compared to the blue one.
But
and
it
therefore
collapses
you
more
also see-
slowly? That's
No.
that's not intuitive there.
No, it is. So what so to do like a fair comparison, we had to plot like the CO2 concentration on a horizontal axis, but time is actually stretched.
Oh,
So
the time is compressed. The time is
yes,
compressed.
so you can also see like
right.
what's on the top. You see like these arrow bars. So you see like what 50 years look like, 100 years, and 500 years between the different simulations.
Okay.
So you need to make some compromise in presenting those. So that of course is very difficult. So in time, of course, the red one collapses faster because it has a higher forcing.
I said you should have a time one as well, just to show.
Yeah. Is it here?
Did I
Do
see
you have one,
point
or
on
is it
there?
in
Yeah, that
supplement?
red line drops slower on a ppm concentration basis, but on a time basis would be falling twice as fast as the blue line. Yeah.
Yeah.
Okay. Wow. All right.
Do you have a time graph or not?
No, but you can actually retrieve the data and plot it yourself.
All right, for the interested viewer, as they say. So let's talk about that a little bit, because now let's match this to reality. You're talking about a 2C temperature increase, and you're talking about a 0.3, the red line here. Is that right? 0.3 per decade increase in temperature. Right now, we've done a lot of discussion on this program about accelerated warming, and the paper that Dr. Hansen and Leon were part of, Global Warming in the Pipeline, which was sort of the first major paper in this area and made these predictions that are all coming true, by the way. And so now we actually have some data, and we realize that we are now currently, and it could change, increase our warming at something like 0.4 per decade. So even more than what you're assuming in your model. And we're also approaching 2C of warming way sooner than the IPCC assumes, which is like mid-century or so. And we're going to be there at 2037. And we're probably going to be at 2.5, which is another number in your paper, but not at the end of the century, but probably around 2050 or so. So what does the real, if you map the real data, and again, it changed quickly before, and maybe it'll change quickly in the future. Of course, 2027 is going to be super warm because of the super El Nino. But assuming that we're going at 0.4 and we're going to hit 2C in 2037 and maybe 2.5C around 2050, assuming those things, what does that tell us about AMOC collapse?
Yeah. So, there were a lot of questions, so I'll start to break them down for you.
Map real data to your paper.
No. So what is good to mention is that with our climate model simulations, so we will get like a temperature level out of that, or even like a critical warming level out of that. But it is good to keep in mind that the warming level that we obtained is you can't translate that to the real world or to the real AMOC. So the 2-degree warming that we found, you shouldn't interpret it like, hey, it is collapsing. It is only demonstrating, like, if you do it at a very slow pace, you can have a stable AMOC, and if you do it way faster, your AMOC collapses. So we also added, for example, a freshwater flux forcing in the background to get a more unstable AMOC. So we're also very clear about that in our climate model simulation. But of course, we want to say something about the actual AMOC. So what is going on as well? So therefore, we referred. So we also cited the Hansen paper as well in our study. So at the very end of our paper, so in the last paragraph, we're actually arguing, okay, what's going on for the real AMOC? Can we say something relevant? Because we know that climate models are biased, so they generally have like a too stable AMOC. So they are very likely to underestimate the real probability of AMOC tipping. But we looked at a few CMAP6 models, so the latest climate climate models, whether they show like a collapsing AMOC, yes or no. And quite a few of them do show that the AMOC becomes unstable around 2060 at the temperature level of about plus 2.5 degrees warming. That is just the multi-model mean, just the average of all different kind of climate models. Some, of course, show like that the AMOC is tipping earlier. Some are projecting that it is at a later stage. But if you just take the average, it happens about 2.5 degrees warming around 2060. So we're currently around the 1.5 degrees warming. So we could actually translate this like 2060 in plus 2.5 degree warming. So if you are heading to that temperature level, you can actually calculate like the global warming level to be en route of tipping. And that boils down to about 0.29 degrees warming per decade. So roughly about 0.3 degrees warming. That can be like a critical warming level for which the AMOC collapses in many of the CM6 models. And then we could refer, for example, to the Hansen paper to see like what is the expected warming. Is it accelerating, yes or no? And then you're actually seeing or observing like the temperature range from the Hansen paper is from 0.27 up to 0.36 degrees warming per decade. So that means that if you believe that those models are correct, then currently we are on track of losing the AMOC in many of those climate models. Also meaning that the probability or like the risk assessment of an AMOC to trigger an AMOC tipping event in the 21st century is therefore substantial. You're muted, Dan.
Sorry about that. You're right. So do you have any probabilities associated with that substantial number?
Yeah, so we actually calculated that in our paper from last August, so August 2025. So what we meant with substantial over there was like triggering an AMOC tipping event was 57%. And then triggering an event before 2100.
Wow.
So that is more than 50% under an intermediate emission scenario. So that is a scenario for which you had about 3 degrees warming by 2100.
It's like playing Russian roulette with more than 3 bullets in the chamber.
Yeah.
Probably so that's not a recommended activity, I think. Okay, so that's kind of mind-blowing. By the way, we didn't really even talk about all the dangers of what an AMOC collapse means. But let's also clarify one thing. When you said unstable AMOC, I think you mean by that crossing a tipping point. Is that right? But
yes.
Even when we cross the tipping point, that is not the time. It's not like it just doesn't fall down and immediately collapse. No. Can you tell us a little bit about the time frame after we hit that tipping point? And by the way, how much lower is that than the regular flow?
Yeah.
How long does it take before it is at a low state?
Yeah. So also in the paper, we use some very careful language because you have like tipping points and also crossing the tipping point, but there is not like a tipping point in terms of temperature in our climate model simulations. So therefore, we always said like starting the onset of the AMOC collapse. So just in layman talks, we will just say you hit a tipping point because the AMOC becomes unstable. So we usually only like in the paper, like these temperature levels or the warming rates, those are the levels at which the AMOC becomes unstable. So we measure always the distance to when the AMOC becomes critically unstable, so hitting the tipping point. So if that happens, no matter what we do afterwards, the AMOC will start to dwindle down in its strength. So even though if we go to like zero emissions again, lowering the atmospheric concentration back to pre-industrial values, the AMOC is in a self-amplifying loop, and it starts to go down all the way to like very weak strengths with any hardly heat transport remaining. So you will get these massive shifts of the climate system, and they do not happen like over the course of 1 week. So like a lot of people have seen The Day After Tomorrow, so the big Hollywood blockbuster, in which the AMOC shuts down, but this happens over the course of like a few days up to a week. Well, for the actual AMOC, it is typically on the order of like decades up to a century. So
Okay.
in 2024, we did like one study in which we just add like fresh water. So that is a very isolated case. And there, the typical transition time scale going from a strong state to a substantially weaker one was about 100 years. Of course, if you still keep on pumping a lot of CO2 emissions into the atmospheres of 40 AMOC even more, that time scale can of course become shorter. So therefore, the typical time scale from a transition from a strong to a weak state is decades up to a century. And of course, for every amount of AMOC weakening, those impacts become larger.
Right.
So even during this very strong weakening phase, you could already experience like the effects to unfold over your own lifetime.
Right. Could be very, very serious. And I call this the mother of all tipping points. I mean, it's like, well, we have done shows where we talk about how bad it could be, but it basically changes the climate all over the planet. It lowers precipitation over the entire northern hemisphere, which affect, and that's where most of the food is grown, because most of the land is in the northern hemisphere. And as you mentioned, makes the thing that everybody knows is it makes northern Europe very cold. But in a sense, that's kind of the least of the problems. Of course, unless you live right there, then maybe it's your big problem. But it also increases sea level on the east coast of the United States by substantially. And that's on top of regular sea level rise. And one of the biggest impacts, from my understanding from what Jim Hansen said, is that all that warm water going to Europe now hangs around Antarctica and accelerates the melt of Antarctica and leads to, as he put it, multi-meter sea level rise around the end of the century, which is pretty mind-boggling to think about. That. So, and plus it just screws up all the monsoons and everything and the Amazon, and it's just a really bad thing. So we should avoid it. Any thoughts? I mean, of course, in your paper, you suggest that one way to try to avoid this is to reduce emissions rapidly. Any other, well, first thoughts on that, because we don't see that happening, and any other suggestions on what we can do?
Yeah, of course. I think this is also kind of like a very big implication of our study. So that's not maybe directly related to science, more due to policymakers, because most policymakers are like interested in the long term, like limiting the total amount of warming. And of course, what policymakers said back in 2015, we need to limit global warming below 1.5 degrees warming, but at most at the 2 degrees level. So that's of course the Paris Agreement. But what we're already discussing, like we are currently, especially I think after the very strong El Nino that is developing now in this year and also going into 2027, we will go again through this 1.5 degrees mark. So we can roughly say we are now at the 1.5 degrees level, and we're at the very high warming rate as well. So 2 degrees is also in reach and not in a good sense. So a lot of people are saying like, okay, maybe we can temporarily overshoot the 2 degree mark. And due to future technologies, we can, of course, extract a lot of greenhouse gases back from the atmosphere into the Earth. And then eventually we are lowering again the global mean surface temperature again under this 2 degree mark. So that are those so-called safe overshoot pathways. So for the Greenland ice sheet and for the entire West Antarctic ice sheet, or just for the Antarctic ice sheet, this can be like a very good option because those systems are so slowly evolving over time. So like overshooting is for like maybe like a few years or a few decades. It takes a lot of time to melt all the ice. So therefore, if you go back again to safe levels, for example, going back to the 1 degree level, you can stabilize the Greenland ice sheet again and also the West Antarctic ice sheet. So that's fine. But for the AMOC, the final warming level doesn't matter that much. That is what we show in the paper. We can have like stable AMOC states up to 5.5 degrees warming. But what does matter is the current warming rate. And if that doesn't go down, you will lose the AMOC along its way. So that shifts your whole perspective from the very far future, so from 2100 to present day. You need to act now. Of course, acting now, like limiting the emissions, would also definitely lower your total warming level by 2100. So that does, gives us like a new conversation with policymakers. You need to act now to limit the risk of an AMOC tipping in the first place.
Although, as we've seen, policymakers are not really interested in doing any of these things. I mean, some are. I mean, of course, but when we have fossil fuel executives in charge of the COP process, and it's the world is not on track to reduce its emissions dramatically. Although we do have renewable energy getting very cheap, we could do all these things. But there is another option for, in addition to overshoot, which, as you're pointing out, overshoot is just kicking the can down the road and hoping other people pay for the technologies of the future and eventually lower our atmospheric greenhouse gases. But there is another way to do it that we can do in the short run, and it's very relatively inexpensive, and that's sunlight reflection methods or solar geoengineering, which would cool the Earth by putting sulfur particles in the stratosphere as one example. And we know it would work because large volcanoes do this a few times a century. Mount Pinatubo cooled the Earth for half a degree for a couple of years and that kind of thing. So since it's not the CO2 concentration, but the temperature change and the rate of temperature change that seems to be the key, do you think that using SRM, sunlight reflection methods, to cool the Earth artificially would help prevent an AMOC collapse?
Yes, so there are a few of my colleagues are working on this because this is like now the Earth is getting warmer quite fast. There are certain regions, they suffer from a lot of heat stress. So people are, of course, now advocating for this, like, okay, if we are breaching the 2-degree warming level, we need to do that, of course, to first lower the heat stress. But this could also be like a viable option to save your AMOC, because then the warming rate becomes smaller again. This can then lead to AMOC stabilization, and you prevent it at the first place. I have seen like a few results from my colleagues. If you do it like too late, then of course you already lost your AMOC because you crossed like a critical warming rate. So you need to do it like right now to limit the warming rate as much as possible. But of course, there is this huge debate about SRM, solar radiation management techniques, because you can also have like negative side effects, changing weather patterns, precipitation patterns as well. So. But potentially, this could be explored if you would do like SRM, like on a very short term, to limit the warming rate as much as possible. Then, in principle, according to our results, you could save the AMOC.
So you can either be pro SRM or pro AMOC collapse. I mean, that's your choice. By the way, that points out, I mean, the fallacy of that argument about the side effects. Of course, there's side effects. No one says there aren't side effects. That's not the question. The question is, what are the side effects of doing it versus the side effects of not doing it? And now it sounds like one of the side effects of not doing it is AMOC collapse. Because, I mean, even if we started cutting our emissions aggressively, it's not going to change very much in the next few decades, the temperature in the next few decades, or even the warming in the next few decades. I mean, because we're not going to go down to zero. It's going to, maybe we're going to turn the corner, but we're at a record high of emissions right now.
So exactly.
Even maintaining that record high without increasing it, it sounds good in some way, but it's really not going to be very good, will it?
Yeah. So we really need to first go to net zero emissions. And that would, of course, start, then, of course, the global warming would level off eventually, but that we're still very far away from that. So, and I think that this debate about SRM will become louder over time because the planet will get warmer. And of course, more and more insights about AMOC stability will show up, also in the climate change. And hopefully we could eventually put like a number on what the real AMOC does under the estimated under the current projections, because that is still like a challenge using only climate models.
And just to clarify one important point, so your graph shows CO2 at the bottom as a measure of temperature, and we're talking about 2 degrees and 2.5 degrees, which are temperatures. But is the actual thing that is causing the AMOC to become unstable the amount of fresh water in the ocean, or is it temperature or both?
Yeah, so the actual destabilizing feedback of the AMOC, so that we had a discussion also last time. So and I think I use your sentence quite often also in different kind of public talks, like the AMOC brings its own salinity to the party. So what global warming actually does, it makes your surface of your Atlantic Ocean like too buoyant. So it becomes way warmer compared to your interior. It becomes too light, so this prevents actually the sinking of the AMOC. And if your AMOC becomes too weak, then this whole salinity advection feedback kicks in. But this salt advection feedback that operates independently of background temperatures, but it can get like a push from global from global warming. So first, what you're actually doing is by heating up your upper ocean drastically, like under current warming rates, you will get AMOC weakening, and this can start off this destabilizing salt advection feedback, and that pushes your AMOC further down.
Okay. And Leon, do you have questions for René? Or
yeah, I think one you said then that politicians are listening, but I wonder whether René has experience with politicians listening to him, like regional policymakers, or because do you have conversations with politicians, or do you mainly speak with your colleagues and sometimes journalists?
Yeah, so I speak with colleagues, members of the public, also reporters, but also with policymakers, also with Dutch policymakers. So our study from last year, in which we also reported like, hey, the AMOC can become unstable at around 2.5 degrees warming in 2060. That also our European, like one of the European members, like Popke Hoekstra. So he's from the climate department at the EU level. So he actually posted something on LinkedIn on our recent study. So it is getting picked up like in all different layers within policymakers. So I think that's a good thing. So people are aware of this, and especially like AMOC stability under climate change, especially from the last IPCC report, there has been like a lot of new knowledge and new insights. So therefore, it was not on the radar before that, and now the field is rapidly developing. Of course, translating all those new science insight into policy, of course, that takes a while. But at least that we have like ongoing conversations with policymakers. I think it's a good thing that the policymakers are getting aware of that, especially also given the impacts. So for the Dutch government, like those impacts that we sketched and lay out in our papers, that is not very good news for Dutch society. So therefore, there is like attention coming from policymakers. But in the end, we need to take like active steps, and that is something what we already know, like the regular climate change, just heating up the planet, that has already like very severe effects. And now on top of that, we're also getting like all this different kind of tipping elements that maybe become unstable. So of course, then we're going to a complete different world. So the current pathways that climate scientists have laid out over the past couple of decades, that should be already enough motivation for policymakers to cut emissions as fast as possible, stay preferably below this 1.5 degrees warming level. But this is clearly not being sufficient because we're still warming up the planet quite drastically. So again, therefore highlighting, cut our emissions as fast as possible and stay below the 2-degree mark, and preferably even lower.
Thank you. And I don't know everything about the AMOC, but maybe you can, maybe you do, maybe you don't. I don't. So does the strength of the AMOC vary during the year? Because I think you had the values in sphere drops, but they can also, of course, translate to petawatts. It's a joule with 15 zeros per second of heat going from south to north. Does that vary over the year? Because you have now, I think, annual averages, but does it vary?
Yeah, so that is something very fascinating. So if you look at the observational record of the AMOC, so a big shout out to all the observational people who are taking those measurements and maintaining them. because there is also a lot of stress on those measurement equipments. Maybe you've also seen reports on that last summer, that a lot of governments are cutting the fundings for maintaining those observational sites. But the longest observational record of the AMOC that we have, like a basin-wide scale, so that we can actually see how much transport is going northward or southward, that started in April 2004. And this is along 26.5 degrees latitude. So that is near Florida, going all the way from the west coast to the east coast. And so there we have like
Of the Atlantic,
very over the Atlantic Ocean, yes. So there we have measurements like 12 hourly. And if you just look at the variability, the AMOC is going over the complete range. So you have very big, large fluctuations, sometimes going all the way up to 35 sphere drops. But there also have been instances that the AMOC was actually reversed, like going to negative values. But we don't quantify or qualify that as like an AMOC collapse, because there is like also a wind contribution to that. And what you see, like after a few days, it's back up again to its mean state. But there is like very short-term variability. So it highlights that the Atlantic Ocean, like the whole system, this very complex current system, is highly variable. And of course, if you take like a mean, a yearly average, then you see like that the AMOC is about 17 sphere drops. And if you look at the observed record of the rapid array, so that is the measurements location, the latitude at which we measure, then you do see like a very slow weakening of about 5% per decade. But good to keep in mind that this one is still not significant, because the observational time series is simply too short with a lot of noise on top of that. So therefore, it is still very hard to say like, hey, this is already a very strong indication for AMOC weakening. So from direct observations, yes, there is an indication of AMOC weakening, but it is not statistically significant. But therefore, we also look at different kind of fingerprints, such as the cold blob or the warming hole south of Greenland. That is like a very important AMOC fingerprint of like a weakening AMOC. So we also published a paper last February in which we discussed like the shifting of the Gulf Stream. So it is going northward. That can also be a dynamical fingerprint of AMOC weakening. The North Atlantic Ocean is also freshening. So there are all different kind of lines of evidence that the present-day AMOC is very likely weakening. And there are also observational records of the AMOC. They are slightly longer. They only look at the deep western boundary current. So like a very big important AMOC branch that is going southward out of the Atlantic Ocean again. So there you have like longer observation records, but they also show that the AMOC in that part is weakening. So all with all, there are now more and more lines of evidence that the present-day AMOC is very likely weakening. And of course, this is also like a very big warming, because that means that we are heading in the direction of the tipping point. I'm not saying that we are already there, but we're not going in the good direction.
Yeah. So if you compare this, the observations, if you compare the observations to all the values almost in your paper, right? The let's say CO2 equivalent rate of increase, the temperature observations, and the corrected. So you also cited Ramsdorff, who corrected for El Nino and other variabilities. And if you look at those temperature increase observation, the rate of increase observations, and indeed the AMOC weakening, it's like pointing, like almost everything is pointing in a direction that it's of the worst case, isn't it?
Yeah. So at the moment, yes, but of course, those emission pathways like RCP 8.5 and 4.5, they're still very close to each other, like until this part. And now from 2025 up to 2050, they start to deviate from each other. So currently, it is very hard to say like which pathway we're still following. So it looks still like the worst pathway. But there are also some good signals, because maybe we are now at our emission peak as a global society. So that is like some good news in all of this. But at the moment, we're still like warming the planet at a very high rate. And of course, this is very bad news for AMOC stability.
Okay.
So if you say we are at reaching the peak, that is like compared to the worst case scenario, it's not as bad as it could have been. I wouldn't call it good news.
No, it's still there's still general bad news in terms of
as long I'll always speak about the AMOC because it's not good news for the AMOC that we are not like it's above your rate, right? It's above your 2.5 per decade rate, maybe close to 5.
I just want to take a quick break and remind everybody, if you're finding this interesting, to please like and subscribe. This is really helps the channel. It helps spread this obviously extremely important message to more people, and helps grow our audience. And it's free, so please like, subscribe, hit the notification bell, leave a comment, and all of those things. You mentioned your previous paper, and by the way, the 3 other interviews we've done with you are linked in the video description below, as well as a link to your homepage and things, and to the research papers that we're talking about today, as well as an easy to understand article about the research paper. So if you don't want to read through the research paper itself, there's kind of a summary and an article from your university. So those all those links are in the description below. You mentioned the Gulf Stream moving north is an indication of AMOC collapse, and it's been a little while since we talked about that. Is there any update on the position of the Gulf Stream, and is it indicating a shift that could indicate a collapse?
Yeah, so I sometimes update the time series myself because, of course, the paper has been published this February, and then, of course, the time series remains static, but data, of course, continue. So I looked at the latest data. There is still a lot of intraannual variability going on, but if you just look at the overall trend, it is still shifting northward on average. It is still significant, but there is not like a drastic abrupt shift observed yet. I think if this would happen, it would probably also be picked up by the media because these satellite observations are retrieved daily, so we can actually monitor the Gulf Stream position on a day-to-day basis. But so far, the Gulf Stream still remains in its southerly path, and hopefully it will remain there, because if it goes, it could indicate that we are close to a tipping point, according to our research paper.
Okay. I have a bunch of other questions about the details of the paper, but I'm going to bring in Stacy now, and she has a question. We'll get one from Eli, and then we'll get a couple of questions from the YouTube audience. And welcome, Stacy.
Hi, great to see you again, Renee.
Hi, Stacy.
And I just wanted to drop in that the Utrecht is also known for one of my favorite things, and that's biking. It's a supreme bike city, and I hope to get there one day. Yeah. Do you bike? Do you bike to the university?
I love biking. I love biking. It's my favorite to go vehicle.
Yes, and it fights climate change. So my thought was a lot like one that's from the audience, and as we've mentioned before, you're a dad now, and what are your adaptation plans? Are you're going to move with your children, or encourage them to move one day, or how does this work in the future?
Yeah, so that's of course again the big problem with global warming and also just general climate change is that of course it is not happening right away. Some things are of course very direct, but it happens over like longer time scales. So definitely, so we also bought a new house here in Utrecht, so we're very happy about that. So we're moving within Utrecht. So like on very short time scales, we do not take like very big measures. But eventually, like to my son, I'm not promoting him to go live near sea like over his lifetime. Especially as for the Netherlands as a low-lying region, of course, we have dikes. We build a lot of dikes, we can withstand like a certain amount of global sea level rise. But if that goes beyond like into multimeters, like maybe over the course like after 2100, then we would probably need to have like a discussion like what are we going to do with all the land? Are we going to make the dikes even higher or whatsoever? So therefore, I would not advise to live there in his late life, and also for his children, so my grandchildren. So like doing like direct adaptation things, well, I don't do that, of course. And also given that the typical AMOC timescale, AMOC collapse timescale is like 100 years. But of course, over time, if we would say like, hey, the AMOC is now collapsing, yeah, then probably we need to make some preparations and also think about those stuff. But we still have time. So therefore, I would say like start mitigating as much as possible, such that we can prevent such a awful worst case scenario.
And the joke, of course, then you have to your kids will be ice skating to work again. Right?
Well, yeah.
Well, was that I think some American politician who said that we are all ice skating to work.
I know. Yeah, I've seen that.
Okay.
We don't get out much.
So let's bring Eli in for a question, and then Stacy will go to you for some YouTube. So, Eli, welcome.
Hi, thanks. So René, for many years it was thought that AMOC collapse would be and would bring with it negative feedbacks or attenuating feedbacks. However, more recently, there's been some research that said no, it actually goes in the other way. It reduces carbon dioxide uptake by the ocean, and the change in albedo in the Arctic isn't necessarily going to compensate other changes in albedo that go along with it. Now, so based on that, a couple of questions. First of all, that isn't really factored into most of the climate models, correct?
Yeah, exactly. Yeah, and it is also very climate model dependent.
Mm-hmm. And so then secondly, and this is maybe I'm going to kind of hold your feet to the fire a little bit. Doesn't that really mean that even though all of us are for emissions reduction, all of us want less pollution killing people, that emissions reductions aren't a complete solution, whether or not as the case, some research found that emissions reductions really stopped being an effective way of addressing this in 2020. So don't you think it's time to start emphasizing not both CDR and SRM?
Yeah, so of course CDR, that would be of course very promising. So that's removing carbon from the atmosphere again, so to lower our atmospheric CO2 concentration. So yeah, people are of course also working on this, but at the moment to have this on a large scale, that is still not that is still very futuristic technology. So we can't rely on that. So the only thing what we can do is of course on SRM. We can do this on a short-term scale, and I think people will be discussing this in the upcoming years, because we know that the temperature is increasing, and also with the super El Nino, or to quote NOAA, the very strong El Nino that is developing, we are maybe reaching 1.7 degrees warming in 2027. So we already have like a sneak view of that kind of world by next year. And people would see, of course, like all those different kind of impacts related to that. So I think people are discussing like, can we still live in this world if temperatures are going even further in the direction? And I think this discussion on deploying SRM in the nearby future, I think that becomes more serious over time. So yeah.
Okay. Stacy, do you have? I'm looking at the chat there too. There's a lot of things there.
Yeah. Well, the one that was kind of funny. Ecom Quest asked if
Time
the
span?
Dutch kids are required to learn swimming because it's
We
on the
just finished
rise.
5 years of swimming class with my 2 kids, so we're good.
Those are good. Okay.
Good luck,
Um,
Renee.
Okay.
And I missed that. What was that?
I said we just finished 5 years of swimming
Oh.
class with my 2 kids, and I wish Renee good luck because his kids are a kid is quite young still, so he still has to.
Okay.
Someone else, Jan, who's in the Netherlands, mentioned that the dikes are in terrible shape because of 2 months of drought. Is that's happening now?
Yeah,
Yes.
we have a very severe drought over just over the large part of Western Europe, and of course dikes are become very vulnerable if it is like very dry as nowadays. So are we already like at the record drought already from 1976? Leon, do you know that?
So it's the warmest summer, and we haven't had we had some rain yesterday, but before that it was like 1.5 months of no rain and a lot of sun. It's a record high sunshine as well, and then the dikes, they start to crack. You can really see the dikes cracking because they need water to keep their structure. Especially certain dikes are stronger than others. For example, of course, if you have these concrete dikes, it doesn't matter much how much water there is. But if you have these peat dikes, they also start to combust. If they dry out, they start to start to have this combustion, and that of course also produce CO2, and then the dikes become very unstable. And with more and more weather like this, of course, the dikes are very much in danger.
So another case of our infrastructure isn't built to handle what's coming, I guess.
And that's for sure.
Yeah.
Hey, let's. I have one here.
And the rate of change of this of the climate
for Renee.
That's also important there.
How closely
Yes.
linked are the AMOC and the subpolar gyre? Would the collapse of the subpolar gyre inevitably lead to the collapse of the AMOC?
Yeah, so this is like a very active research field. Like, how are those like intertwined with each other? Because they are two separate tipping elements. And what you see with in most climate models, if the SPG, so the subpolar gyre, goes, eventually, or the AMOC follows, like the AMOC tipping event follows. So we also published a paper on that, on which I was a co-author. So that work was led by Sieber and Drijfhout. So it was also published in August 2025, and there you saw first like a collapse of the subpolar gyre. So the subpolar gyre has like these very deep convection cells, sometimes down to 1 to 2 kilometers into the deep sea. So a lot of mixing going on. But this also shuts down, and that is then followed by an AMOC collapse. But there are a few climate models that show like an AMOC tipping event, but still having like active deep convection sites over your subpolar gyre. We also have a result of that. So we don't know for sure yet. It looks like, because they are connected, but its relation is very complex. But for now, I think there is quite a lot of evidence if the subpolar gyre collapses, because it works in some similar way as an AMOC collapse. So if the subpolar gyre collapse, it is overall not like a very good sign for your AMOC stability.
I have another,
and that can also and that can also happen on much shorter time scales. Like then we're talking like more like below like 10 years.
SPG?
So it's like in Europe, yes, the SPG can collapse on a very short time scale. And it is like its little brother in terms of impact. So you can already have like some local cooling, and if then the AMOC collapse follows, then you get like the very big cooling also over Northwestern Europe.
Okay.
There are a couple questions here that my immediate response would be no. I think that's confusing things, but they might be that. It's about air travel, and how is that affected in relation to is the jet stream Are those fluctuations affected by the AMOC?
Well, the jet stream is, and that is also something what we see nowadays. You have this cold blob sitting south of Greenland, so that is the important AMOC fingerprint, and this can already cause the jet stream to shift in its position a little bit over that part of the Atlantic Ocean. So the jet stream can be influenced by the AMOC. We've also seen if the AMOC is actually collapsing, it also shifts the jet stream a bit. But of course, that signal is then very pronounced. But to say something like really about the jet stream, because of course the position of the jet stream is very noisy. So to make like a very clear case, hey, like the current AMOC weakening is already displacing the jet stream, you can of course argue that. So there's a lot of natural variability going on as well.
Okay,
That's
so
right.
it's not like air travel will become dangerous or more dangerous with the AMOC as it shuts down or weakens.
Well, if it shuts down, what we also found in our climate model simulations is that if it shuts down, you get like a stronger temperature difference between equator to pole. So, and this in general strengthens your jet stream, and of course that can also cause like more turbulence, and of course that can of course impact air traffic flights.
You're going to need more air sickness bags on the plane. So there's an interesting comment question. Well, it's too long here, the way it shows up. But I don't really want to read the whole. I'm going to turn that off and just read part of it. It was just like summarizing. You want to understand if you understood the whole talk. But in it, he has the sentence, AMOC collapse this century is possible, but not presently the scientific consensus. And certainly not something we can say is happening now. From what I can tell, the scientific consensus among those who work on AMOC, which is not all climate science, it's a specialty, seems to be that there is a consensus that the AMOC is on track to collapse this century. Wouldn't you say, or am I wrong?
No, I would completely agree with you, because there are also a lot of interesting studies from my peers, international colleagues, that are working on that, and they are also giving like sometimes they do have like different answers to them. So what I think this new recent study, what it actually shows that these different perspectives within the AMOC tipping community, that you can have like stable AMOC states under extreme climate change, and you have like collapsing AMOC states under like low emission scenarios. So those results were both correct, and they are like unified under the terms it is due to the rate-induced tipping event.
Okay, so your current research, the one we're talking about today, is linking these disparate other studies showing different results. However, your study shows that it happens under certain conditions, and those are the conditions that are reality.
Yes, so that's also reality.
That we are in a
but
more likely than not in a collapse state this century, unless we take drastic action that we're not taking now, certainly.
Yeah, and so there are, for example, like there's also this very famous Baker study which was published last year. So they showed like, they argued, hey, you can have like a stable AMOC state also under extreme climate change, and that is also something that we are also briefly mentioning in the paper, is that a lot of climate models have like a way too stable AMOC. So they have like only one state under its given configuration. So no matter how far you push your AMOC in terms of CO2 or climate change or whatsoever, it will always, or is always getting attracted to its very strong state. So of course, if you add like 4 times CO2, your AMOC is weakening quite rapidly. It stays there, but eventually it does recover. So based on those results, you can say like, hey, your AMOC is very resilient, but probably your AMOC is in the first place in an incorrect regime. So it is not stable enough, and therefore it is very likely underestimating the risk of tipping in the first place. So we have also a lot of papers on that. We have a very good theoretical understanding why this is the case. A lot of climate models do struggle with AMOC stability or sensitivity. So they do get like the correct AMOC strength. So that's a good thing. But in their tuning like making these climate models, which is like a very complex task. During their tuning of their AMOC, they lost the stability. So most climate models have a too stable AMOC, but there are also still results out there for a few climate models. They do not show like a collapsing AMOC, and they are also part of the entire climate assessment, also from the IPCC. So therefore, we should of course have like an ongoing scientific debate about these things. But most work that I've seen so far, like they all indicate like, hey, we need to have like a new assessment in the next IPCC report, especially on the AMOC tipping part, considering like all the evidence, all the papers that have out been there, like the ones that do show like, hey, the AMOC can collapse, but also the ones they don't, to have like a proper reassessment. And I think what the IPCC does, like in the previous statement or assessment, they say like it is very unlikely that we would hit this. I think they will reassess it, and given also the new evidence that is out there, I would not say they say like, oh, this will be the case, but I think they will say like this is not as unlikely as we thought. So probably they will increase it, but I will leave that up to the IPCC.
Well, speaking of that, Jim Hansen years ago came out and said that the AMOC was likely to collapse around mid-century, and he said the reason is, well, first of all, you sort of give two reasons. One is, there's a lot of melting in Greenland ice sheet, more than people think, or more than was assumed, I guess. But the other reason he said is that the models that the IPCC uses assumes ocean mixing is less or more than it really is. And those models that correctly show ocean mixing do hindcasting better than the ones otherwise. And so he said, but once you throw in the right ocean mixing, you see, oh my God, the AMOC's collapsing. So I got a couple of questions. Is that right? And two, in your models, do you have the right ocean mixing in them?
So I'm not entirely sure about ocean mixing, but I'm familiar with those hindcast models. But there was also a new study published. I think it was also in the first part of this year. So it was a study from Portman and colleagues, and they looked, for example, at all those different kind of biases. And if you take the models and you bias them in the correct way, your AMOC projections will get much lower. Like, going from a standard about 30% weakening, they go down to 50% weakening.
In other words, higher chance of AMOC collapse if you use
exactly
more. When you say bias, I mean models that hindcast better. I mean that show the past more accurately.
Yeah, of course. That is, of course, if you also have these kind of models and you include those, and you will get like a worst estimate for your AMOC tipping or your AMOC weakening. Of course, that is also then again bad news. So that also, like, to really answer that question, which is relevant for the public, for reporters, for policymakers, we need to improve our climate models to get like a very realistic AMOC strength and AMOC stability. But saying that is relatively easy to do so. And also, again, a big shout out to my colleagues for those who developed like this big climate models, because it's a very difficult task, and to get everything right, that is simply like not possible at the moment. But with new future technologies, like also developments within the field, maybe quantum computing or whatsoever, maybe we can get like a breakthrough, and that will definitely lead to a better assessment on AMOC stability.
So
there's a question from Jean that I am very curious about as well, and that's they're concerned about life forms in the Atlantic and how this might affect extinction rates and illnesses. Will it cause a mass die-off, or will it be slow enough for adaptation?
Yeah, so this is also a very good question. So what are the impacts on marine life and ecosystems and whatsoever? So I'm definitely not an expert on this. So I refer here to my research from my former colleague, Amber Both. So she's now working in Denmark. So she is looking, Amber Both.
Amber Both.
Yeah, it's also really fun to invite her as well. So say hi to me. So hi to her if you speak to her. But what she actually showed is like if the AMOC shuts down, you also get like migration of fish species and whatsoever. It is an overall loss also for the fisheries as well. And we also have like these shipping logs from Iceland, in the 20th century and also in the 19th century. So you had like these very big events of like cold spells, and then also all different fish species, they went around the island in certain places. And of course, sometimes fisheries are dependent on them, and they also lead to to more risk in their food security and their food supplies. So, and this is of course on a very local scale, only on Iceland. But now imagine that, for example, your entire Atlantic Ocean cools. So certain fish species may migrate southward. So your whole food chain also gets under pressure.
That's what Iceland call it a national security risk, right?
Yeah.
Mm-hmm.
Sorry,
so
go ahead.
René, what's your what research are you working on now? What can we expect to see from you shortly?
Yeah. So our new research, we're doing again a climate impact study. So in 2023, we published a paper in which we're exploring like what would AMOC weakening do with the North Atlantic hurricane season. So what we actually found is that under AMOC weakening, also under climate change, you will get like less North American hurricanes. So you could say like, hey, this is a good thing. Of course, in terms of hurricane risk, yes, but elsewhere you had like more like a more increase of tropical storms. But we found like overall that under climate change and AMOC weakening, the hurricane frequency drops. But it is still very hard to disentangle both of them. And like in a new study that we're currently working on is that we can make this very nice assessment, like what is coming from global warming and what is coming from an AMOC collapse. And then we can actually say something about like a future hurricane season in the very far future, if the AMOC were to collapse, of course, if. But then we can actually make like some kind of quantification what the impacts are on the lower latitudes, so the deep tropics, of hurricane formation, genesis, and intensification, which is of course also very important for those. So we primarily focused so far for Northwestern Europe, and it is also nice to shift a little bit the perspective to the deep tropics.
I think climate deniers will latch onto that and say, hey, look, AMOC collapse is great. It lowers hurricanes or something like that. But anyway, well, first of all, good luck on all of that. And maybe we should leave if you on this, if you could spend 30 seconds or a minute with policymakers, global policymakers, and you wanted to tell them a bit about what your research says they should be thinking about, what would you tell them in a very, and again, these are policymakers, they don't understand the science too well and everything, but they want to hear from you. So what would you tell them?
And are they a policy from the EU or just the global level? Or
no, you get to speak to the. We actually form an international coalition to fight climate change. Sometimes the Ministry of the Future or something.
It's like a Ministry of the Future, perhaps.
Yeah. But something we're taking it seriously. All of a sudden, maybe the Super El Nino whacks everybody on the side of the head and wakes them up and say, "Oh God, we got to do something." But they want to hear from you about AMOC, and what are you going to tell them?
Well, I would first start with like very basic thing. Like the science is clear. We know that the planet is warming. Cut our emissions, mitigate as much as possible. That will make the planet livable, even though we're still going to higher temperatures. And now imagine a world in which like all like the bad scenarios come like true. So we want to avoid it as much as possible. And that is just spreading the very broad message. And then of course I could also like highlight a few things, what would happen, for example, for Europe, for the tropical regions, like a lot of stress in terms of food security, because the tropical rain belts are shifting. This can also give rise to more international conflict, what also climate change is doing. So this list goes on and on and on, all the bad things on AMOC tipping, and it can also trigger. We also had this discussion about Antarctica, this cascading tipping points. Maybe it could also add up like more sea level rise due to basal melt near West Antarctica or whatsoever. That is, of course, still like a very big topic of discussion. So yeah, we need to avoid this in the first place.
Okay. All right. Get our ass in gear, I guess, whatever, and get working. René, thank you so much for again joining us and informing us. You make a very complicated topic understandable, so thank you also for that. And it's also it's a little crazy that such an important topic is getting almost no coverage. I mean, it's not zero, but you know, compared to other things happening in the world, which are also important, but are not going to have the long-term impact that this has. It's a little strange. Well, we're going to do our part to spread the word, and thank you for helping us with that. And for everyone out there, again, please like and subscribe to Climate Chat. We have a really bunch of interesting shows coming up in the next couple of weeks. I'll just give you a little hint. Next week, it's on Doomers. And the week after that, it's with Adam McKay again, the producer director of Don't Look Up, and a very interesting op-ed that he wrote a little while ago about the biggest climate lie. We're going to talk about that. And so
we'll have a famous doomer on next week.
And we have a very famous doomer on next week. That's true. So everyone's going to want to listen on that as well. And so, and with that, everyone, please, thanks for joining us. Like, subscribe, and all of that. And we'll see you next time. Thanks. Bye-bye.
Bye.
Thank you. Bye.
Bye.